Oh, alright, so welcome back to another fun-filled, action-packed, non-flipped Algebra 2 classroom video with me, Coach Goo. Today, notes number 3. Everyone's days are a little messed up, but ours is notes number 3. Today we're going to be focusing on transformations of exponential functions, okay? The concept of transformations is not new. Like, we've already done this multiple times. We did it with quadratics, we did it with absolute value, we did it with square roots, transformations. This is the 4th time we're going to be doing this concept, right? So, you know, for some of you guys, 4th time is going to be a charm. So, the objective, let's just write something down here for our objective. We're going to be able to, hopefully, identify, apply, and graph transformations of the exponential parent function, which is f of x equals b raised to the x, where there's some limitations on b. Does anybody remember b can't be a certain number? Do you remember what it is? That's right. B cannot equal 1. And also, b can only be a certain type of number. What is that? It has to be positive, which means it's greater than 0. Wow, it's like you already did this class or something. That's crazy. Okay. So write that down. So with that in mind, guys, I want you to take a look at these examples right here. You don't have to write this down. This is just to get you to think a little bit. But the parent function is always, listen to this, this is important. A parent function for exponential, it's always just a base raised to the x. It's always just a base raised to the x. The base can be any number that fits the criteria, but it's just a number raised to the x, okay? That's exponential. So, if our parent function is f of x equals 2 raised to the x, here are some different transformations. Remember, I told you, you've seen all the transformations before. These concepts are not new. So, with that in mind, I want you guys to take a guess, an educated guess about what each of these equations does to the parent function graph. So right here, f of x equals 2 to the x plus 3. What do you think that does to the graph of the parent function? Just take a guess. What do you think it does? How does it move the graph?
Does it move it up?
Move it up how many?
3.
Exactly. It moves it up 3 units. Very good. So then down here, what do you think this minus 3 one does?
Down.
Moves it down 3. Right. Remember, even with the other transformations, it's always, when you add or subtract a number just at the very end, right? That's moving it up or down. And this is no different. Same thing. So now we can write our rule as going to be f of x equals b. B is just the base. It can be any number. Raised to the x plus, we're going to add d. That's going to call that one d. This is going to move your graph vertically. Vertically means up and down, right? Vertically, d units. So write that down. So now, let's take a look at this right column right here. You see on the right column, we have f of x equals 2 raised to the x plus 3. We're adding 3 to the x. What do you think that does to my graph? How does that move my graph? To the, what'd you say?
Left or right?
Which one is it, left or right?
Left.
Left 3, right. Remember, horizontal movement is always opposite of the sign. Very good. So then on the bottom one, when it says f of x equals 2 raised to the x minus 3, how is that moving? To the right 3, exactly. Very good. So we can write our rule now. It's going to be f of x equals b to the x. And how do you show that your movement is opposite of the sign? You put minus in your equation. So x minus c. And that's going to move your graph horizontally. That means left and right. C units. But in parentheses, I'm going to put opposite of the sign, right? Because you want to make sure that you know if it's positive, you're moving to the left. If it's negative, you're moving to the right. All right, so let's take a look at this last example. The column in the middle, it says 3 times 2 to the x. You see that one? 3 times 2 to the x. What do you think? What transformation do you think that shows? Putting 3 times 2 to the x. Think about the transformations we learned about, we've done before. What are you saying? What are you whispering over there? A stretch or a shrink. That's right. So that 3 in the front is going to be a stretch or shrink. What do you think it's going to be, stretch or shrink? Well, do you think it's going to be vertical or horizontal? Why do you say vertical? Outside of what parentheses? So you're right. You're right in saying that's vertical, and you're right saying outside because, we have this concept of inside or outside of the function. But what would be inside? What do you think is meaning inside? Okay, I don't really know what you mean by that. Okay, so notice the 3 right there is at the very beginning of the whole equation, right? Where's x? It's up here, right? So if it was going to be horizontal, it would be in front of the x, like this. Okay, technically that's going to be our inside when it's attached to the x right there. But this 3 is on the very front, not attached to the x, that's going to be vertical. Okay, so if it were up here, that would be horizontal. But in the very front, that's vertical. Okay, so now you said it's vertical, so is that going to be a stretch or a shrink? Stretch, that's right. By what? By 3, exactly. A vertical is straightforward, remember? Horizontal is always the one that flips things around. So if this top one is a vertical stretch by 3, what is the one under it where it says 1/3 times 2 to the x?
Shrink?
Vertical shrink by? That's right. Good. And there's one more thing we need to add on. What if this value a right here was negative? What do you think the negative would do? Reflect over the x-axis. That's right. Good. So now we can write our rule. F of x equals a. Here's that value in the very front. A times b to the x. And if a is negative, then what do we say it does? Reflects over the x, that's right. As we abbreviate into rocks. If a is between 0 and 1, what does that show? That's right. You don't got to whisper it. Vertical shrink. Right, if a is between 0 and 1, it's going to be a vertical shrink. Because when a is greater than 1, that shows what? Right, it's a vertical stretch. Yeah. So we got all the rules written out. So now we want to be able to actually graph this. So let's do some examples of graphing. I'm just going to do two complicated examples with you. That way you'll see a little bit of everything, Doing a very simple example is kind of a waste of time. All right, so up here we're going to do f of x equals -3 times 2 to the x. All right, hang on a second. Hold your horses. Now remember, when we graph these, right, we're going to use a table to be exact, okay? Now, the table is going to be x, and then f of x, right, is going to be your parent function. So, can you tell me what the parent function of this equation is? 2 to the x, that's right, nice. You actually got it, there we go, 2 to the x, very good. Because remember, not many people could answer this today, but the parent function is the base raised to x, okay? So a lot of people always looking at it and they're like, they don't even know what to take. But yeah, it's just the base raised to the x, so it's 2 to the x. That's your parent functions, right? And so that number is going to change based on what your base is in a specific problem. All right, so do you remember the 5 numbers we always use for x? What are they? Nice, good. There we go. And now we're going to find the y values by plugging in the x. Okay, so how I recommend doing this is starting from 0, then doing 1 and 2, because those are very straightforward. It's pretty simple. And then negative ones will follow after that. So, whoa. Hello? Stop moving, please. All right. Okay, so if I plug in 0 for x, we get 2 to the 0. What is 2 to the 0? 1. Anything to the 0 is 1. There we go. Next, what if I plug in the 1 for x? 2 to the first. 2 to the first is 2. Oh my goodness, wait a second. Okay, that's... Everybody else is saying this too, right? Okay, and then... Please stay, thank God. Alright, so then 2 to the 2. What is 2 to the 2 going to be then? 4. So it's very easy to find, the positive numbers, right? So now we go to the negative exponents, because some people get confused with the negatives, but once you found the positives, it's very easy to find the y values for the negatives. All you have to do is flip your fraction. So what's the negative 1 value going to be? 1 over 2, right? And then what is the negative 2 value going to be? 1/4, right. Notice positive 1 was 2, negative 1 was 1 over 2. Positive 2, we have a value of 4. Negative 2 is 1 over 4. There you go. Okay, so now this is where this is the part where we tell the transformation. So Jaime, what was the transformation you said? Reflect over x. That is right, because the negative sign in the very front tells us that. And what is the next okay, please. Vertical. What? By? Oh, sorry, vertical stretch by 3, right, because it's greater than 1. Good. So now we're going to apply these transformations to our table. First, we've got reflect over x. What would that do to my table values? Which ones? Wait, what do you mean by that? That's the inverse. That's not the same thing. Yeah. Reflect over x, what do we do to the values? Which ones? X or the y? Y, that's right. Reflect over x makes the y values negative. So instead of positive 1/4, we have negative 1/4. We get negative 1/2. We get negative 1, negative 2, and negative 4. That's the reflect over x. Our next transformation is vertical stretch by... Wait, what? By 3. Right, vertical stretch by 3. What does that do to my table values? Times what? Which ones? So it's a vertical stretch, right? Which values are vertical? X values or y values? Y's, yes. Remember the y-axis goes up and down, so it's going to have to be the y. So vertical stretch by 3, we're going to multiply all the y values by 3. All right, let's see if we can multiply these numbers. What is negative 1/4 times 3? Negative 1/4 times 3. You just multiply straight across. Yeah, negative 3 over 4. Because remember, the 3 is just like a 3 over 1, right? So if I multiply it straight across, negative 1 times 3 is negative 3. 4 times 1 is 4. So then what is negative 1/2 times 3? Negative 3 over 2. What is negative 1 times 3? Negative 2 times 3 is? And negative 4 times 3? There we go. So here are our values. Now we have to graph it. And this is where some people get confused because we've got fractions. But they're all y values. They're just values on my graph. So the first point we have is negative 2, negative 3/4. So watch this. Negative 2, I'm going to go left 2, 1, 2. And then negative 3/4, that's between 0 and negative 1, right? It's not all the way to negative 1. It's between. So it's about right here. See, it's like 3/4 of the way between 0 and negative 1. Next, we've got negative 1, negative 3/2. Negative 3/2 is the same thing as negative 1.5. So we're going to go left 1 and then down 1.5 units. So 1 and then half. That's right here. What's the next point that we have? 0, negative 3. That one's easy right here. Then we've got 1, negative 6 right here. And then 2, negative 12 is off the page. So like this. There we go. Something like that. Notice it's reflected over the x-axis. It's going down now. And it's very steep because of that 3 in the front. All right, so there's a couple of things we want to identify here. First thing we want to identify is the asymptote. Who knows what the asymptote for this graph is going to be?
0.
If you just write 0, that is not correct.
Y equals 0.
Y equals 0, right. Is this line right here. And the equation for that line is y equals 0. All right, now we're going to do domain and range, but we're going to do it in set builder. So what is the domain of this graph? That's right. So it's negative infinity to positive infinity, but how do I write that in set builder? Can you tell me what's right? Squiggly line first, and then? 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 That's right. And then? And there you go, right. This is set builder. And doing this is going to make it very easy to write the range, okay? So that's the domain. Squiggly line, squiggly bracket x such that negative infinity is less than x, which is less than infinity, squiggly bracket. As for the range now, so I'm going to start off the same way with the y and such as, okay. So how we like to think about the range on the y, by the way, if you want to make this note to yourself, you can, but the domain is always the same. The domain is going to be the same on every single exponential graph. But the range is going to be different. And how are we going to do the range is take a look at what line is kind of the cutoff line. Do you see the cutoff line? You literally graphed it. It's the asymptote, right? Asymptote is like the cutoff point. So pretty much you know the range is going to be y, and it's going to be something involving the value of the asymptote, the 0, right? Now you just have to tell, is it going to be greater than? Is your graph greater than or less than the asymptote? Less than, yeah, you see the graph, it's below, right? That means it's less than. All the y values are less than. So your range is going to be what? See ya. Y is less than 0. That's right, just like that. Yeah, that's it. That's it for the range. Last two things we're going to identify is x-intercept and y-intercept. What's the x-intercept? What? None, right. Because it doesn't. It's never going to touch the x-axis. You wrote the asymptote as y equals 0. What about the y-intercept? What did you say?
0,
Okay, 0, negative 3. Very good. That's how you give the right answer as a point. You know, no matter how many times we say it, every time you write just the number, it's going to be wrong. It is a point. 0, negative 3. That's where it crosses the y-axis. Very good. Okay, let's turn to the back side because I'm actually going to use one of the graphs on the back because, you know, kind of out of space a little bit. So I'm going to use this very last graph right here. This time we're going to do y equals 1/2 raised to the x minus 4 plus 3. Okay, so let's start off the table right here. X. Now, can you tell me the parent function of this equation? The parent function. 1/2. 1/2 to the power of x, exactly. Remember, it's just the base raised to x. What is the base here? 1/2, and then you just put raised to the x. Everything else is a transformation. All right, so the x value is the same as always, -2, -1, 0, 1, 2. So as I recommend, we always start with 0, go 1 and 2, and then go to the negatives. So if I plug in 0 for x, what do I get? 1/2 raised to 0 is 1. Right, anything raised to 0 is 1. Good. What if I plug in the 1 then? 1/2 raised to the first. It's 1/2, right. The power of 1 doesn't change anything. So then I plug in the 2, so 1/2 raised to the second is going to be 1/4. That's right, 1/4, because it's 1/2 times 1/2. So now it should be easy for us to go in the opposite direction, right? If the positive one is 1 over 2, what would the negative one, if I plug in negative 1, what would that give me? 2. 2 over 1, which is just 2, right? What would my y value be at negative 2 then? 4, that's right. Just flip the fractions that we had down there. There we go. I'm going to erase this to make it a little clearer. There we go. So these are our parent function points. Now we're going to identify the transformations. Can you identify the transformations in this equation? To the right 4, right? This minus 4 tells us to the right 4. Very good. And then up 3. If this plus 3 at the very end tells us up 3. Very good. Uh-oh. All right, cool. So now we got to apply these transformations to our table. So what does right 4 do to my table values? What? Add 4 to which values? X or Y? X, that's right, because right is left and right, horizontal, which is X. So right 4. We're going to add 4 to all these numbers. So what is 4 plus negative 2? 2. What is 4 plus negative 1?
3.
0 plus 4. 1 plus 4. 2 plus 4. There we go. We got one more transformation to take care of, and that is the up 3. And what would that do to my table values? Up 3. It would change your y value. In what way? Add 3, that's right. So up 3. We add 3 to all the y values. Let's see if we can get these numbers right. Plus 3 plus 3. What's 4 plus 3? What's 2 plus 3? What's 1 plus 3? What's 1/2 plus 3? 3.5. Exactly. What's 1/4 plus 3? 3 and 1/4. Yeah, you're just adding 3 to that fraction. So these are our points. Let's see what this graph looks like. First point we have is 2, 7. That's going to be 1, 2 to the right, up 7. That's right here. Next point is 3, 5. So to the right 3 from the origin and up 5. Boom, right here. Next one's 4, 4. And now we've got 5, 3.5. So we're going to go 5 to the right from the origin. So 1, 2, 3, 4, 5, and up 3.5 units. So here's 1, 2, 3. Then I need to go up 1/2. So it's right here. And the last one is going to be 6. So we go 6 to the right. 1, 2, 3, 4, 5, 6. And up 3 and 1/4 units. So 1, 2, 3, and then 1/4 is just barely above the line. And so this is what the graph's going to look like. Notice it has moved, and it's not as steep as the other one because there's no 3 in the very front. So you want to draw the asymptote. Where should I draw the asymptote on this graph? Y equals 3. Right, you can see from the graph that it's approaching this line right here. So your asymptote is, as you said, y equals 3. Very good. How did you find that out anyways? How did you get y equals 3, Aiden?
I don't know. I just kind of looked and I saw that it didn't ever go below 3.
Right, so you just looked at the picture and you found out, right? Yeah, so that's one way you can do it. Now, but notice this. On our first graph that we did up here, right? Did this graph, the first one that we did it move up or down at all? No. So the asymptote's y equals 0. Remember, it's always y equals 0 for the parent function, right? But now look at this one that we just did. Did this one move up or down at all? It moved up 3, right? And how did that change the asymptote? Yeah, you just added 3. So the relationship between how your graph shifts up and down is your asymptote exactly. So if your graph shifted down -5, down 5, what would your asymptote be? Y equals -5. That's right. If your graph moved up 20 units, what would your asymptote be? Exactly. Nice. So now let's do domain and range. Now, what did I tell you about the domain? It's always the same, so we can just copy down that first domain. Negative infinity, less than x, less than infinity. But the range is different. What's the range on this one going to be? Does anybody know? Y is greater than 3. Right, the cutoff point is 3. That's the asymptote. But is our graph greater than or less than? It's greater than because it is above that line. There you go. Nice. All right. Do we have an x-intercept? No. So the x-intercept is none. And I'm just going to tell you the y-intercept because it's way off the page. If you plug in 0 for x, you can find the y-intercept, right? But it's going to be 0, 19, actually. That's what it would be. It's when x is 0. All right, so that is this graph. Right here. All right, so there's one. Okay, we got the graphs down, so that's good enough for the graphs. Let's try a different type of problem. Let's try just identifying from the equation what our transformations could be. So right here, state the name of parent function and the transformations. So this example is going to be, let's see here, y equals -4 times 3 raised to the x plus 7 minus 2. So notice it says we're going to state the name of the parent function. Now what does that even mean? Remember, there's different families of functions, right? And you've seen on like the test before where they give you different types of functions and you have to tell the transformations. So some of the different types we had are linear, quadratic, square root, absolute value, right? And sometimes on those tests people just write random stuff, like things that I've never heard before. So we need to know the names of these functions, okay? So what is the name of this function that we're working with? Exponential, right? This has been on the title of every single notes page we've done so far. Exponential. That is what this type of function is called. Because your x, your variable, is in the exponent spot. And now we're going to list the transformations in order. So what is the first transformation that you would do here? Reflect over x, right? That negative sign at the very front is reflect over x. Nice. 2. What's the second transformation you see here? What? What kind of stretch? Vertical, right? Vertical stretch by 4. Okay, what is the next transformation you see after that? Left, 7. And the last transformation you see? Down 2. That's correct. Very good. Nice. All right, you guys seem pretty good at that one. So then the last thing that we need to be able to do is match equations with graphs. So down here, it's actually there for you. So what you want to do here is first identify the transformations that are happening in the equation, right? Then use hints from the graph to actually find your answer. So looking at the first equation, what transformations would happen in this first equation? All right, what like tell me the transformations, not the answer. Vertical stretch by 2? No, there's no vertical stretch there. Remember, that's the base, right?
Yeah.
So there has to be a number in front of the base for that to be. So right, this is just left. Left 1. And? Yeah, hang on a second. I'm just trying to get out of this thing. Please. All right. up 1. Okay, so the first hint that you can look at, right? Remember, when a graph moves up or down, that changes the asymptote, right? So this graph moved up 1. So the first hint we can look at is, do you see a graph whose picture has an asymptote that moved up 1 unit? Which one? Just A. Look, this is the asymptote here. At y equals positive 1, right? Yeah. The other ones, they moved down 1, right? So right away, you know that the answer has to be A. There we go. Because of the asymptote, it moved up 1. Okay, so let's move on to the next ones then. On the second equation, how did our graph move? What are the transformations there? Oh, the first one moved right 1. Why did I left? No one corrected me. Come on now. Left 1, down 1. That's right. So, how can I do this? Because both B and C, we see the asymptote move down 1, right? So that's not enough to give us our answer. So does anybody know how we could find the answer? What? Which way it goes horizontally. So how can you tell?
Because from 0, right from the normal function.
Right from the normal function. So yeah, that's a good way to put it. It's either going to move right or left from the original function, right? What point is always on the original function? 0, 1. So look, watch this. If I put 0, 1 as my original function, right? Then I have to move left 1 and down 1, right? Let's see what happens when I move left 1 and down 1 from that original point that's 0, 1. If I move left 1 and down 1 on B, where's that? Move left 1, down 1. From the 0, 1 point. It's right here, right? I moved left 1 and then down 1, right? That's not on my graph though, right? Let's look at my other one, C. If I move left 1 and down 1, where do I end up? Right here, right? That's on the graph. So that's the only one that makes sense, right? Exactly. Because once I applied those transformations to C, that's where my graph ended up. So C. And you can also test this theory on the last one as well. Because watch this. The last one, how does the last graph move? Or the last equation? We already know the answer, but let's just prove it. How does it move?
Left 1.
Not left 1.
Right 1.
We're opposite of the sign. Right 1 and then?
Down.
Down 1. So if I take my original point, 0, 1, and I move it down, right 1, and then down 1, it should land on my graph, right? So if I move it right 1, down 1, look at this. B, it lands on my graph. C, it doesn't, right? So that would let us know that B is the transformation from my parent. Right 1, down 1. So A, C, and then B should be your answers. And that's pretty much all the topics that are covered on these notes for transformations of exponential functions, guys. So, until next time. See you then. Peace!